Okay, so we'll go ahead and get started. So today's topics are these. We're going to talk about the generalized uncertainty principle, and then the time evolution of expectation values, and we'll try to recover the classical equations of motion in a sense from here. And this will conclude chapter 5, and then we move on to the beginning parts of chapter 6, which is perturbation theory, approximation methods. And the first one is the subspace projection method. And then if we have time, we'll talk about the time-independent perturbation theory. Okay, so we'll get started with the generalized uncertainty principle. So last time we defined for some Hermitian operator that corresponds to an observable, okay, we can compute its expectation value with respect to some state. Okay, and we'll write this for short, and we denote it by a bar. Okay. So the physical meaning of this quantity is if I prepare a lot of identical systems and I do the same measurement on each of them, then on average for the observable A, I'm going to get a value of a bar on average. So now we can define a new operator denoted by delta A, which is we subtract the average of this operator from it. Okay, so obviously now this operator has 0 expectation value, but the use of it is to study the variance of the operator A. Okay, so we could compute the expectation value of this operator, which would be this is, you have no doubt seen this in probability theory. And typically we define a standard deviation of A as the square root of the variance. Okay. So this operator encodes information about the uncertainty. Yeah, loosely speaking, the standard deviation is the uncertainty that we have in that operator. And so this encodes the information about uncertainty. So now we can consider two Hermitian operators. Okay, A and B. Okay, and let's say that they do not commute. So we construct their commutator to be written invisible. So why do we include this I here? The reason is that obviously a commutator is going to be anti-Hermitian, right? Because if I write this out, it looks like this is the commutator. Why write it out. Okay, if I were to take its adjoint, right, we're going to switch the order here, and then because they're all Hermitian, right, so the adjoint becomes which was minus the commutator, right? So the commutator is obviously anti-Hermitian. Now if you find this C with an I, then I'm assured that the C is still a Hermitian operator. And Hermitian operators are easy to deal with. So this is how we define C. Now we consider these operators, delta A and delta B, and they're defined as we subtract the expectation value from the operator itself. Okay. So now we're going to start with some arbitrary state phi. And we'll say that the action of this operator on phi is to take it to some other state, f. Okay. And then the action of the operator delta b on phi takes it to another state g. Okay. So if we started with a normalized state and apply these operators, the resulting states would not be normalized in general. Okay. And we can investigate their norm. Say the norm of f, okay, when I write it out, okay, using direct notation, it's going to look like you will have the Hermitian adjoint here. But because this is self-adjoint, it's Hermitian. So we get that the norm of this state F basically is equal to the variance of A in phi. Okay. And similarly, the norm of G would encode information about the variance of B in the state phi. Okay. Now we can also study their covariance, which is clearly is going to be okay. So now we will make use of the Schwarz inequality. Okay. So the Schwarz inequality for functions on this what we're working with is called a Hilbert space. Is defined as this. Everybody is okay with this inequality. So this is a general property of vector spaces. So now, if I translate this to direct notation.
Why don't you relate that to the cosine inequality then?
All right.
Before I relate it.
So if we consider the vector space that we're most familiar with, which would be the vector space of the three vectors. Okay. Or three vectors. If I have, let me do it. Okay. No, actually, let me do it. Okay. This is equal to the magnitude of A, magnitude of B, cosine theta. Theta being their the angle between them, right? And this is clearly because cosine theta is bounded by plus minus 1. Okay. So this is clearly, I could say that. If I did this, okay, this is clearly less than just A and B. Okay, so this is the Cauchy inequality for three vectors. And when the dot product becomes integrals, they're called Schwarz inequality. And because we're in Hilbert space, the inner product is defined with this. You have to complex conjugate it first. Okay, so these two are kind of an extension. Okay, so now translate this into the direct notation. We get okay. So now if we plug in these for each term, then we have put a lower bound on the product of the variances. So this will be and we don't need to bother writing these magnitudes. And why is that? These are Hermitian operators, so their expectation values must be real, right? Must be real. So their squares must be positive. We're not worried about the magnitude squares thing. Okay, so this is just sigma A. And this is just sigma B squared. So by writing this, we have placed a lower bound, okay, which is sort of the covariance between these two operators. Will be the lower bound of the product of their variances. Okay. So now we turn to evaluate this because this is not in a form that's easy to work with. But we try to evaluate this covariance by relating it to the commutator. Okay. So now, although A and B, and delta A and delta B by itself are all Hermitian operators, but their product is not necessarily Hermitian. Especially when they don't commute, it's guaranteed not to be Hermitian. Okay. So, but I can always decompose this into two parts. Okay. I can construct a clearly Hermitian part. Okay. And plus a clearly anti-Hermitian part. Okay. So everybody clear with why each of them? This is Hermitian, this is anti-Hermitian. Okay. So now this is just the commutator of delta A and delta B, right? Okay. So what would be the commutator of delta A and delta B? Okay. If A and B commutes with IC, right, and if I subtract a number from A and B, they still commute with C, right? So it should be clear that this is just equal to okay. So now if I consider the expectation of this thing, okay. Now I take the expectation value of this operator, it's Hermitian, so I know that this part must be real. Right? So I'm going to get a real part coming from here. Okay. Now C is a Hermitian operator, so its expectation value is real again. Right? But then I multiply by I, so this part is going to be imaginary. Right? Okay. So now if I were to evaluate the magnitude squared of this thing, right, I'm going to get just the real square plus the imaginary square. Right? So this would be 1/4. Let me write this line out entirely. Because these are all real numbers, I just put squares on them. I don't worry about the magnitude square. Alright, so now this is clearly, because this is a real number, and the real number squared is clearly a positive number. So I can conclude that this term is clearly larger than just the imaginary, just coming from the imaginary part. Alright. So now if we further relate this to the Schwarz inequality, we get that the lower bound is greater or equal to this value, okay, which is further greater or equal to just the expectation, 1/4 of the expectation value of the commutator. Now because the state that we have chosen is arbitrary. So in the final form, we don't want to leave this arbitrariness. So we can conclude that for any state, this is true. So we can just write okay. And now if I were to all of these are real numbers. Right? So now if I were to take its square root, I get that the standard deviation, or in quantum mechanics, we loosely call this just the uncertainty, okay, is equal to 1/2 the expectation value of the commutator. Okay. So to give you an example, let me if we had the operators x and p, right? And we know that they commute as xp is equal to IH bar. That's their commutator relation. Everybody should remember this. Okay. So now, if I plug this in, that would mean that sigma x, sigma p is greater than or equal to 1/2 h bar. This is probably the most famous uncertainty principle. Okay. But you'll see that if we started with any two dynamical observable that corresponds to a permission operator, then if they don't commute, we can use this generalized formula here to construct to study their uncertainties. Okay. So now this is the generalized uncertainty. So now let me move on to the next topic. Are there any questions so far? Okay. So now we'll study the time evolution of expectation values. So we said that this expectation value of an operator can be defined with respect to an arbitrary state. So now if we consider a time a state that is time dependent, then its time evolution would be time dependent as well. And so I'll denote the time dependent state is this. Alright, and to interpret this, you must remember that if we're talking about expectations, then it only makes sense if this time and this time are the same. Okay. So now I can study the time derivative of this thing. Alright, and to do this, we just simply make use of the product rule. Because so far we have assumed that the observable A, the operator, has no explicit time dependence. Okay, in that case, then you can take this time derivative right across A without doing anything. Okay. And then only take time derivative of the states. Okay. So now you recognize now these terms, okay, I can relate them to the Schrodinger equation because the time dependent Schrodinger equation written in direct notation will look like this. So clearly I can replace the time derivative of the state with with this. So if I go ahead and plug this into here, we get that the time derivative, part of time derivative of the expectation value of the operator is equal to. Okay, so if I write this, okay, and now I'm going to write its adjoint. So you turn the bra. This is called a bra, okay, and the other side is called a cat. This is called a cat. And over here, you turn the bra into a cat. But now the operator is going to operate on the right of the bra. Sorry, this is called a cat. Let me make that clear. So this is called a bracket, right? Right. So if I were to divide this word into three parts, right? So bra, a cat. And we're left with a C. That C stands for, I think, you can think of this as a complex number. Okay? Because when you take the inner product of a bra with in general another cat, okay, then you're going to get in general a complex number. Okay? So this is how you should remember it. Okay? bracket, the middle C stands for complex. Okay. So now the operator operates on the left of the cat and on the right of the drum. Okay. So this will turn into I over H bar. This, and the Hamiltonian is Hermitian, so it's adjoint to itself. All right, so now I plug this into there. Now this is just I can take out a common factor of IH bar, and then there will be a minus sign because the minus sign here. All right. So now, because expectation values are additive, right? I can combine these two by just taking the difference between these two operators. Right? So let's erase this. Now, a matter of convention, although this is certainly true, conventionally this is written as let me forget about the T, the phi, but remember that we're talking about time-dependent states. Okay. So the time evolution of the expectation value of the operator is governed by the commutator of this operator with the Hamiltonian. Okay. So if you remember at the start of the semester we talked about Poisson brackets, right? And we used this notation, Poisson brackets, and in classical mechanics, the time evolution of a dynamical variable was governed by the Poisson bracket. Okay. Now this is in a sense reminiscent of that. Okay, but not exactly yet, because we're talking about expectation values. Okay. There is also a way to do this by talking. If I think about the operators as being time dependent, okay, there's an equivalent way to formulate this without the expectation value, but we'll get to that later. So now,
go from the nonsense that was in the last one.
here.
Yeah.
Right. So I'm just saying, because the time-dependent state was arbitrary, so I just use change of notation.
Okay.
And now, because I want a minus sign out, okay, I just switch the order. Okay. So now, let me give you an example. Okay, let's consider a really simple Hamiltonian, which is the Hamiltonian for the one-dimensional Schrodinger equation. Okay. So it will look like written in terms of the operator P and S. Alright. So strictly speaking, the potential would also be an operator, but I don't want to denote it by an operator because that would mean writing too much hat. You can just understand that the potential is a simple algebraic function of the position. Okay. So now let's consider first the time evolution of the expectation value of. Now, because we're in one dimension, right, so this is like dBt instead of the target. Let's consider this. Okay. So basically, this amounts to calculating the commutator of x with the Hamiltonian. So the Hamiltonian has two parts, right? The kinetic energy and the potential energy. And the potential energy is just a function of x. So an operator will obviously commute with its own function. So now why is that? And let me say that it commutes with a nice function of itself. And you can think about it as certainly an operator is going to commute with any arbitrary power of itself, right? Because this would amount to x minus. Okay, right. So this is certainly true. Now for some nice function that has a Taylor expansion, I can always Taylor expand that function with, say, with respect to 0. Then I will get a power series, right? In terms of the different powers of n. Right? So since the x will commute with each power, it must be that the x will commute with the entire function. All right, so this is certainly true. So computing the commutator of x with the Hamiltonian just amounts to computing the commutator of this. So is everybody okay with this? Yeah. So now let's write down the commutation relation between x and p. So what does this relation allow you to do? Let's write it out explicitly. All right. So now, just by simple algebraic relation. So written in this form, it tells us how we can take the x operator across p. Okay. You take it across to form this, but you just add in a factor of the commutator. Okay. So it's really simple. So now, if I wanted to take x across xp p squared, okay, I just take it across once. Okay. I write down p x p plus I h bar p. Okay. Is everybody okay with this? Okay. So now I take it across twice. Right? P squared x plus so really this is just twice of I h bar p times plus p squared x. So now if I move this across to this side, we get that the commutator between x and p squared is just equal to twice I h bar p. Correct? Okay. So if I divide by 2m, I'm going to get now if I plug this into this equation here, okay, now what does that say? I is going to cancel with minus, I should produce 1. Okay.
You're missing an m in the denominator.
I'm sorry. Right. So this is just b, right? So we get that ddt of the expectation value of x is just the velocity. The expectation value is velocity. So we can write so if I go back to the convention of denoting, the expectation value by bar, okay, and I want to stress that this is in general a function of time. Okay. So you see that the expectation value obeys the classical equation, at least for Newton's first law, right? This is Newton's first law, right? So then we can consider Newton's second law by computing the commutator of p with the Hamiltonian. Right? So that will give you the time evolution of p, the momentum, which is Newton's second law. Okay. But you'll see there's some difference. Okay. And that difference is the difference between quantum mechanics and classical mechanics. Okay. So let's try to compute this. So once again, because the Hamiltonian is quadratic in p, right? The p obviously commutes with the second power of itself. Right? So this amounts to calculating the commutator with a function of x. Okay. So this is not an obvious thing to do. Okay. But let me point you out to something over here. So what we computed here is that the commutator of x with the square of p is equal to, let me put this into a more enlightening form. Okay, I can write IH bar. 2p is just, okay, if I did a symbolic derivative, this would be it. And what is IH bar? This is just the commutator of x and p. Okay, so for simple power functions, we get this condition. So this is something interesting. What we can do with this again is, now suppose we had a really nice function of x, and that would characterize most potential. We had a really nice function of x, and we're going to differentiate it. Okay. So we can make a Taylor expansion of x about 0, right? And that would give you v of x is equal to v of 0 plus. Because we're in 1D, it's perfectly fine to write this. Evaluated at 0 times, this is the linear term, right? And then the quadratic term. And so on, right? And now, these are just numbers, right? Because I evaluate the derivative of this function symbolically with respect to the operator x, and I evaluate it at 0. These are just numbers. So they don't affect commutation relations. So now if I try to commute p with each of these powers, I will get that derivative relation, right? So in general, I can write that x and p, if they commute, the commutator of x at the nth power of p is going to be n times IH bar. Okay, and why is that? Because when we take x across, right? So you can think about computing the commutator as taking x across n powers of p. Each time I take x across 1p, I'm going to write IH bar, right? And then because I need to multiply by the other powers of p that's remaining, right? So that I get a p to the n minus 1. I need to take the x across n p's. Right? So there's an n factor here. Right? And this is just the commutator of x and p times the derivative. Okay. Right. So now since this works for each power, and we have expanded this as a power series, it must work for v as well, right? So in general, we can write p of x would be, I just plug in this equation here. The commutator of p and x times the derivative of the potential with respect to x. Okay. And what is the derivative of the potential with respect to the position? To the coordinate. What is this? Yeah, it is the force, right?
The first line, shouldn't you do also px to the power of n if you want to apply the first line to the second line?
No. Well,
Your Taylor series expanding your p, aren't you?
Right.
And then your Taylor series expand your p in terms of power of x. So
Right.
your first line should be commutation of p with the power of x.
Oh, I mean, when you change these things, yeah, sure, you can do this.
Yeah.
Yeah, but I mean, the example given here, I'm trying to commute x with the power of p, right? But that doesn't change anything. You just change this commutator relation, which is just minus. Okay. So we have succeeded in computing this, and this is just this is p and x is going to commute with h bar over I. Okay, right? Minus IH1, right? So I can certainly define a new operator that is called the force operator.
Okay.
And it should be minus the force, right? Okay. So now I plug this into the equation of motion here, right there. Right. I can say that the time derivative of the expectation value of P is equal to, now that minus IA squared is going to come in. Minus IA squared, this cancels. So this is equal to the expectation value of the force operator. So this almost looks like Newton's second law, right? Newton's second law would be written as in terms of the expectation value, if we take these to be classical quantities, the Newton's second law is certainly written in this form. Okay? But going from here to here, okay, there is a difficulty, right? Because we know from probability theory, can you just take the expectation value inside of a function? You can't. So this is not in general equal to the function evaluated at the expectation value of things. So you can see that in quantum mechanics there will be, even in terms of expectation value, there will be deviation from the classical case. Okay. And we can make light of this by considering, sorry, this should be not equal to general. We can make light of this by considering what is the difference between these two. Right? And to do that, what do we do? What do we do? Taylor expansion again, right?